Welcome. In part two of this introduction, I would like to talk about how to think about a model delay and throughput in a network such as the internet. So we talked about packet switching. So packet switching is the process by which one packet switch forwards a packet it has received to the next hop on the path to the destination. We talk about transmission delay. Transmission delay was the time that it takes for this packet to be put or pushed out onto the link. Okay, so if the link has a capacity or bandwidth of R bits per second, it would take L divided by R seconds to push it out, where L is the number of bits in the packet. Now, suppose what happens then? This packet then will eventually, after some delay, be received by the next hop in the path, who then has to receive this packet, store it before it itself can then forward, push this packet, send it to the next stop in the destination. So this is done through a process called store and forward. So store and forward here means that the entire packet has to arrive at the router before it can be examined and sent out that link. Now in this case, the transmission delay is paid again, is encountered again. So in a system that uses this approach, store and forward, the cumulative delay from the source to the destination will be the transmission delay along each of these links. So if they had the same bandwidth, it would be n times this transmission delay. Yeah? So in this small example here, the end-to-end delay would be 2 times L divided by R, because it only shows 2 links. This is done if the technology used is store and forward. I'll point out that some switches also have the ability to do something that's called cut-through switching or cut-through forwarding, where parts of a packet can already be sent out across the next link even before the tail of the packet has arrived. So in this case, a packet that's being pushed out here, when it arrives here, part of the packet may already be leaving even before the tail end of the packet has arrived. Cut-through switching is typically used by um, so-called Ethernet devices. It comes with its own set of problems. For example, if something goes wrong, if a checksum failure is detected, um, but it is a technology that has the advantage to at least potentially avoid this accumulation of transmission delay. Besides transmission delay, there are other sources of delay that contribute to end-to-end delay that are important to understand. A key source of delay is called queuing delay. Let's see how that comes about. Suppose we have a situation where a node A wants to send data to node C and node B wants to send data to node E. They are connected through a shared link that packets that go from A to C and B to E have to travel. Now suppose further that this link here has a smaller capacity, maybe only 1.5 megabits per second, than either of the links from A and B to this shared element. So in this case, what happens? Well, only one packet can be transmitted on this link at a time, either one of those green packets or one of those blue packets. So they have to take turns, and the way this is done is through a queue. This router maintains a queue of packets if a packet arrives, and if this link is currently busy, then these packets are being added to this queue, and this queue is then served, and these packets are being sent out. This queue is typically served in a FIFO order, although other policies can be applied as well. This falls on the so-called quality of service. But fundamentally, what can happen here is queuing, and the time that packets spend while sitting in the queue, waiting to be transmitted over the next link, this time is called queuing delay, and it adds to the delay that a packet has end to end. Okay, so queuing delay is a source of delay in the internet. Also, what happens if this queue is full? Queues are finite, right? We cannot afford to spend unbounded amount of memory to maintain these queues. In this case, packets are simply dropped. So if B sends a packet and encounters this queue is full, maybe the queue is full because too many packets arrived in too short of an amount of time, and so they couldn't be sent out across this slower link, then these packets are being dropped. And in this case, the network will make no additional effort to somehow retransmit these or so. That is up to the application, the internet. So the network provides a best effort service. If a packet is lost, perhaps due to queuing, then it is the application's responsibility to retransmit this packet every once. In fact, so the queuing loss is one of the major sources of packet loss. The other one would be if there were bit errors that are detected by checksums. But the internet makes the assumption that bit errors are much more rare than losses due to packet loss. At least that's the case for wired networks. It's a little bit different in certain wireless environments. But that's the key assumption. In fact, internet protocols are designed such that if they sense packet loss, so if they see that packets are not arriving, they suspect that it is due to queuing loss, and they suspect then in fact that this link is overloaded, and then they back off and send at a lower rate. Okay, so this is queuing delay. It's the second source of delay. On this slide, I'm showing all four sources of delay. We already talked about transmission delay, and I talked about queuing delay. What are the others? Well, first of all, it takes some time on each of these elements for the data that is being sent there to be processed. That's referred to as the nodal processing delay. Maybe bit errors need to be checked, and it may also take some time to look up a packet's header in the local forwarding table to decide which link to send it out to. This goes under nodal processing delay. The queuing delay is the time that a packet may spend in the queue, which depends on the congestion level of the router. What about this fourth one, propagation delay? So we'd already talked about transmission delay, right? Transmission delay, that is the time it takes for a packet to be, we say, pushed out onto the wire, right? And that depends on the transmission rate. So if we have, for example, 100 megabit, gigabit, or 10 gigabit Ethernet, and of course the number of bits that we're sending. But this fourth delay, propagation delay, is the time that it takes for the signal to propagate across this medium to the other side. So signals do not propagate instantaneously. And also this propagation delay does not depend on how fast we're sending bits. So this can be quite subtle to understand. Okay, so the propagation delay, what does it depend on? It depends on how far this element is apart, so the length of the physical link, and then the propagation speed in this medium. This propagation speed is not the speed of light, by the way. It is a fraction of the speed of light. This is the so-called velocity factor. And a good rule of thumb is maybe it's 2/3 of the speed of light. It varies depending on whether it's copper or um, what kind of fiber optical medium it is. But let's say a good ballpark number is maybe 2/3 the speed of light. What does that mean? It means that the geographic distances that are covered by the internet can lead to quite significant delay. For example, say the United States from West Coast to East Coast, maybe 2,800 miles, so let's say 4,000 kilometers, right? Then to go from the West Coast to the East Coast, okay, just the propagation delay would be as much as 20 milliseconds. Okay. This delay is in addition to the transmission delay, right? The transmission delay can be made shorter by using a higher bandwidth, but the propagation delay cannot. So if you have that, then for a round trip, what would round trip be? It would be 40 milliseconds. Okay. Now suppose somebody created a protocol where each packet that's being sent needs to be responded to with an acknowledgement. Then to receive acknowledgement would take 40 milliseconds. That means you could only send 25 packets per second. So clearly that would not be very, very efficient. Most of the time, this link would actually be unused while you're waiting for your response to come back. The way out of this is to make sure that you're sending multiple packets back to back even before you receive the reply, so that that you don't have to wait for a reply before sending the next packet. Okay, this is in fact what internet protocols such as TCP do. Okay, they're called, for that reason, they are called pipelined protocols. So and then a way to think of this is we can think of these packets as they travel the network, kind of like little buses, right? Okay, so these buses they go at a certain speed, which is the propagation delay, and then they carry these bits, yeah, and the width of that bit is determined by the bandwidth. Okay, so if we have a slow network, then the bus may look like this. Each bit takes a large amount of time. If you have a fast network, then these bits are sitting back to back as they travel across the link. There's some nice animations on the textbook author's website, the network textbook that I'm using here to visualize this effect. But the key thing to remember is that a faster network, okay, with more megabits or gigabits does not equate does a shorter propagation delay, because the propagation delay depends on physics, the length of the physical link, and the propagation speed in this media, things that by and large we do not have control over. But yet they significantly influence the design of networks. Um, what about this queuing delay? So the queuing delay that occurs when packets wait in a queue before they can be transmitted depends on, of course, how quickly packets can be sent, right? So that is the bandwidth of the link. It also depends how big those packets are, which is the number of bits in them. But it also depends on the rate at which they arrive, the average packet arrival rate. In fact, the quotient of, if you multiply this with the ratio of L times R, we get what's called the traffic intensity. So if this traffic intensity is small, okay, then the average queuing delay would be small, so queues would not form. And if this traffic intensity is greater than 1, that means that on average more packets arrive that can be sent out that link. In this case, queuing must occur, and in fact the queue will grow longer and longer, and the average delay would in fact be infinite in this case. So here supply would exceed capacity. Um, the interesting part is what happens if this traffic intensity is less than 1 but approaches 1. Okay, this is the part that's shown here. So at this point, what happens is the average queuing delay can actually already grow. And that is because the arrival process of these packets is typically it's a stochastic model. It is a stochastic process, can be modeled as one. And very often it's the case that these packets do not arrive in lockstep. Okay, and so the arrival overlaps somewhat, queues form, and in this case, as the traffic intensity approaches 1, the queuing delay already grows, right? If they arrived in lockstep, that wouldn't happen. Let's say if we had a system where, on one link a packet arrives, then another packet arrives, then the first one arrives, okay, then in this case, in fact, we could send at all times a packet out to the link and no queuing would occur until we exceed the link capacity. But that's not what happens in practice. In practice, we may have one packet arriving, then maybe the other one arrives here, maybe the next one arrives here, and then maybe some overlap that leads to this queuing effect, where the average queuing delay can, in fact, grows unbounded, can be shown as this approaches 1. This is also an effect that we know from road traffic, right? Okay, so traffic intensity low, then it's like on the autobahn, and as the traffic intensity grows, then we get a traffic jam, and a traffic jam tends to occur even before the road reaches its theoretic capacity. And things like on-ramps that, for example, display a green light every so often, attempts to bring traffic more into lockstep to make it so that the capacity of the road can be reached without these effects occurring. So this was about delay, right? So the time that it takes for a packet a bit after it's been sent to be received. But throughput is a measure where we're asking how many bits can be sent during a certain amount of time. Okay, those are different measures, right? Here we're looking at over time what bits can be sent. The throughput, in fact, depends only in the asymptote, only on the transmission delay, as long as the link can be kept busy. Okay. Um, so it's distinct from the latency, the amount of time it takes after some data has been sent for it to be received. Right? This is how much can be pushed through over time. We can look at instantaneous throughput. We can look at average throughput, the rate over a longer period of time. And a good way to model this, to think about this, is in terms of an analogy, which is actual pipes that carry some kind of fluid or liquid. So if a pipe can carry a fluid at a certain rate, that is the same as, or like saying it has a transmission rate of a certain number of bits per second. And so suppose what happens if we have a small network, which is two links, where a server sends bits into a pipe, and there are two pipes from the server to that intermediate link element, and then to the recipient of different capacities. What will the throughput be? And here our intuition, in fact, applies. Okay, which is that the throughput will be the smaller of the two, right? So that is, if this is a larger pipe here, the first one will be the bottleneck, and otherwise the second one will be the bottleneck. In fact, we call this the bottleneck link. So the bottleneck link is what constrains end-to-end throughput when traffic passes through a series of links. So now you may wonder, what is the bottleneck link when you access a web page, right? Or access some server somewhere. So in this case, there will be some link that connects the server to its edge route in the access network, some uh, link capacity that connects you to your edge router, and then somewhere in the internet, um, the bottleneck link will be there. Now, within the internet, of course, there are multiple connections that are in use at the same time. And there may be a connection between this server, for example, and this client. So these connections, these streams of packets may share some links. So there may be one link that is shared by all the connections that are shown here on this visualization. So then the question is, what's the bottleneck link? And also the other question is, what portion of the available capacity of this shared link does each of these packet streams get? And the answer to that is that roughly this link is shared fairly between the different connections, and here specifically TCP or TCP-like connections. And so if there are, let's say, 10 connections go through there and they fairly share this, then each would essentially obtain a tenth of this connection. And then the question is, so what's the bottleneck would then be the smallest of the server client and this bottleneck link. In many cases in practice, it will be the so-called last mile, that is the connection to the access network that is the bottleneck. And the reason is because these network here are typically run by um, large companies that perform traffic management and network planning, making sure that their network can handle the load of their current customers, and that plan years in advance to make sure that they keep up with growth. That's not always the case, but this, what it says, is often the bottleneck. The updates at the edges of the networks happen much less frequently, right? So this may be an update, for example, the fast Ethernet to gigabit Ethernet, or perhaps switching to a new generation of cable modem or fiber to the home technology. That's why that's in practice often the case.